Okay, so here we are again. We just finished looking at A star, and before that we have looked at various algorithms which search for paths in the state space or in the plan space. Let us start by trying to generalize the different algorithms that we have seen. So, the algorithm that we have seen is branch and bound, A star and best first search, and what we are going to see now is WA star, which falls under the generalization that I am going to talk about, and we will try to look at these 4 algorithms under a unifying framework. So, the framework that I am talking about is to do with 2 aspects of search. One is the pull that the source has on the candidates, and this pull is realized in particularly in the algorithm branch and bound, which tries to stick to as close to the source as possible. The other is a push, and the push is towards the goal state, and this is something which is experienced only in best first search. And as we saw, A star algorithm combines the 2 aspects, and we showed that consequently it finds the shortest path. But let us try to look at all these algorithms in one framework and in fact generalize it. So, we consider the function f of n is equal to g of n plus w into h of n, where w is a weight that will determine how much importance we give to the heuristic function. Now, g of n represents the pull factor, where it says that we want to minimize the cost of coming from start node to the node n, and h of n represents the push factor, which says that let us get on towards the goal as early as possible, and let us choose a node which is as close to goal as possible, or it appears to be as close as to the goal as possible, because the heuristic function is only an estimate. And w will control how much importance we give to the heuristic function. Now, at one extreme you can say that w is equal to 0, that means we just do not give any importance to the heuristic function, and we only give importance to the pull to the source, and we have only in mind that we have to find the shortest path essentially. And you know that if you put w is equal to 0, f of n becomes equal to g of n, and that is the algorithm branch and bound or Dijkstra's algorithm that we had considered earlier. It only is worried about staying as close to the source as possible. At the other extreme, we can say that w tends to infinity. When we say w tends to infinity, we are actually trying to say that the weight of g of n is 0 or negligible, but in this one framework we can just express it by saying that w tends to infinity. If we had 2 weights, one for g of n and one for h of n, we could have said that the weight for g of n is 0, but equivalently we can say that the weight for h of n is tending to infinity. That means it is much more important than g of n. Then we have only the push towards the goal that is being active, and what is in the task is to find the goal as soon as possible. The task is for that we have speedy termination, and we saw that if we put w equal to 1 here, we would get A star search, but we can choose different values of w, and we will choose 1 today just to see what is the effect of that. Now, look at this very small example where we have 2 goals, 2 paths from start state to the goal state. The start state is the leftmost node and the goal state is the rightmost node, and every horizontal edge has a cost of 12. I have not written them for the rest of the edges, but we will assume that they are all of cost 12. The diagonal edges are either 24 or 36, as you can see here, and if you just think a little bit about this, you will see that this is essentially the edge costs have been chosen so that they are about 120% of the Manhattan distance between those nodes essentially. This is because we want to eventually have a admissible heuristic function. Our heuristic function, which is going to be the Manhattan distance, will underestimate the cost to the goal essentially. Okay, so let us first consider what best first does. That is the algorithm that we had started looking at it, and the best first is what uses the Manhattan distance. So, for the first two nodes that are generated, which are this one and this one, best first has to choose one, and clearly it will choose the one with the lowest heuristic distance, which is 60, because the other one is 70 as you can see, and it will expand that. Once it expands that, it will generate its child, which is of cost 50, and clearly you can see that this process will go on. It will go from 60 to 50 to 40 to 30 to 20, which is what is the heuristic value of this node, to 0, which is the heuristic value of the goal. So, the best first search algorithm will simply shoot off in the path which is on the top and will not even consider the path which is at the bottom. I have carefully chosen these two paths, so that they are actually of equal length. So, if you inspect them also, you can see that there is a kind of a symmetry about these paths. The actual path cost is same for the both, but our algorithm best first search only goes down one path and ignores the other. That is because its starting point in the top path is closer to the goal, and it simply prefers that. Now, if you look at branch and bound only considers G values. G values are in these shaded nodes, as you can see. The first node will have G value of 24 in the bottom graph, bottom path, and 36 in the top graph, because that is the edge cost. So, it will choose the bottom node which has a value of 24 and come to the second node which has a value of 36. Now, this value of 36 is going to be equivalent to the value of 36 here on the top node, and now it has to choose between them. So, since we assume that the choice is made arbitrarily, it will choose one of them and generate its child. The child will be longer. In both cases, it will have a cost of 48, as you can see here. So, it will go back to the other node with the value 36, then it will look at both the nodes with value 48, then it will look at both the nodes with value 60, and so on and so forth, and explore both the paths before it terminates with a value to the goal, by picking up the goal. The behavior of A star is similar in nature. The values that you see inside the circles, these are F values as computed by A star, which, as you can now realize, happen when the weight is 1 essentially. So, f of n is equal to g of n plus h of n. Now, the first two nodes have a value of 94 and 96, as you can see. 94 is obtained by 70 plus 24, 70 is the heuristic distance and 24 is the edge cost. Likewise, 96 is also computed in a similar fashion, 60 is the heuristic distance and 36 is the edge cost. So, it will obviously choose 94, exactly like what branch and bound does, and generate its next child, which is 96. So, now we can see that both these nodes have the same f value. So, it can choose either one of them, and not only that, as it moves forward, their children also have the same value. So, the f values, they increase as you go towards the goal, and this increase happens because your estimates are becoming more and more accurate. The underestimating heuristic function has less to do, because you have already covered part of the path. So, as you go from left to right in this graph, which means as you go towards the goal, the heuristic values increase, and in this particular example the heuristic values decrease, the f values increase, and in this particular example they again increase in sync. So, from 96 at the next level they go to 98, and at the next level they go to 100, then they go to 102, and eventually find the path to the goal, which is of cost of 108. So, the behavior of A star in this particular graph is identical to the behavior of branch and bound. It visits the name nodes in the same order, and it may find either the top path or the bottom path, but you can work that out that it is more likely to find the bottom path, because it will find that path to the goal first with a f value of 102. When it expands, it will put the goal on open with a value of 108. It will expand the node with 104 also, but it would not have found a better path. So, the parent of 108 will remain 102. So, A star will find a path from this direction. Now, what about W A star? That is the algorithm that we want to look at now, and we look at the value where weight is equal to 2, and the values shown in these gray boxes are the values where f of n is equal to g of n plus 2 into h of n. So, for the first node, for example, on the top the value is 156, and this comes because we take 60 in, it is 36 plus 2 into 60, and that comes to 156, and for this node it is 24 plus 2 into 70, and that comes to 164. Now, you can see that 156 is the lesser of the two, and when it generates its next child, it gets a value of 148, which is again lesser than the node of 164. So, on this graph, W A star with W equal to 2 behaves exactly like best first search. It shoots off on the top path and continues till it reaches the goal and terminates, and the algorithm never proceeds beyond the node on the bottom path essentially. So, you can see that here is a small example graph where there are two paths to the goal, both paths are of equal cost, but it is just that their topology is a little bit different. The top path is closer to the nodes are closer to the goal, the bottom path the nodes are closer to the source, and both best first and W A star, they take the upper path and without looking back they just go ahead towards the goal. Whereas branch and bound and A star, they look at both the paths alternately. So, they look at one node in the top path, one node in the bottom path, then one node in the top path, and so on. They explore the graph much more diligently before saying that okay, we have found a path to the goal, and the path, as we have shown in the case of A star and also in branch and bound, which is Dijkstra's algorithm, is the optimal path. So, now let us look at a situation of the problem that we have been looking at so far. The same example that we saw for best first and A star, we now look at it from the perspective of W A star, where W is equal to 2. So, you can see that the values that have been written on the next to the nodes, for example, this 150 is 160 is 2 into 80. So, the 80, as you can come, is the Manhattan distance, and the value that the node will consider, the algorithm will consider, is 160, which is twice the Manhattan distance, because the weight is 2 essentially. So, what I have done is I have pre-labeled the entire graph with 2 into Manhattan distance values, so that it is easy for us to simulate, hand simulate the algorithm essentially. Okay. So, we now trace the progress of weighted A star over this graph. Okay. So, as before, we start off by expanding the start node. You can see that the start node has a value of 200, which is the value that the weighted A star gives to H. So, H is actually 100, if you remember, and this 200 comes because we do 2 into 100 essentially. And likewise, this value of 257, for example, has been got by 37 plus 2 into 110, and likewise for the other nodes. So, as before, the orange nodes are the ones in the closed. We take up the action after the first node has been expanded, and the cyan nodes are the ones on the open. And as before, we will keep marking the best node on cyan by this red block arrow that we have, and W A star is going to expand the nodes. So, initially of course, we have seen that all the algorithms that we have seen have chosen this particular node and expanded that node. So, the behavior is similar to that, but from here onwards the behavior of the different algorithms varies essentially. So, best first search and A star had both seen this node with a value of 173. A star had seen this node with a value of 192, which was 90 plus 12, which was 102. So, A star would have picked this one, but W A star picks this one, and also the best first search picks this one. And if you have gone through the example of branch and bound which I asked you to do, you would see that even branch and bound would pick this node essentially. At this point, the behavior of the best first and W A star changes. Best first would have chosen this value because it is closer, and if you remember, best first in fact from here it sped off towards the goal without looking at this node with a value 192, which W A star is still looking at, and the reason for that is that W A star also looks back like A star. It takes into account the cost of reaching the node as well, and you can see that the path that best first has found so far is a expensive path. It is 21 plus 12 plus 33, whereas A star had found the shorter path, which is of 2 edges of length 12, and W A star also does that essentially. So, best first would have expanded this node with a heuristic value of 80 or 2 into heuristic value being 160, but A star looks at another node which is on open, and then it finds a cheaper path to this node which has now come down to 184. The heuristic value does not change, of course, the f value changes. The f value is defined differently. It was 226 before W A star expanded the node with a value 192, and it becomes 184 after that essentially. Then of course, it expands this particular node, and as we have seen, this particular node which is going to be the next node to be picked by W A star is a favorite of all algorithms, all heuristic algorithms, because it appears to be closest to the goal, and as you can see that because this distance is short or even the Manhattan distance is small, all algorithms have a tendency to pick this node, and we had seen that this was a kind of a dead end because there was no path going from this node except to the node that we are visiting now, which is has a value of 206. So, again remember that this 206 has come by adding up the cost. So, what are the costs here? 12 here, 12 here, 22 here. So, G of n is 46 plus the heuristic value was 80. So, 2 into 80, and that gives us a value of 206, and that is the smallest of all the cyan nodes, or in other words smallest of all the nodes on open. And then the W A star algorithm, which has a greater push factor, it has a greater effect of heuristic value, now heads off rapidly towards the goal, and along the same path in which best first search also went, and finds the goal this thing without exploring the path which either branch and bound or W A or A star would have done. What happens as a consequence is that it has found a different path. The path is different from both from A star and also from best first. So, if you remember, A star had found the path of course 148. We will do a quick comparison next. Best first had found the longer path. Best first had found the path which was going like this, which was obviously much longer. It had a cost of 195 or something, whereas W A star finds a path in between. It is the cost of 158. It has seen 9 nodes. 9 nodes have been inspected and put into closed, which is less than what A star did, but it has found a more expensive path than A star. So, one thing to observe here is that even though this algorithm has a flavor of A star in the sense that we use both G of n and H of n, because of the excessive weight given to h of n, the heuristic function has become something which is not admissible. Remember that we had said that A star is admissible as long as the heuristic function underestimates the distance to the goal. Now, clearly when we multiply the Manhattan distance by 2, it is not going to underestimate the distance. So, that property of heuristic function being admissible is lost, and as a consequence we can see that W A star has found a path which is more expensive than the optimal path, but it has found it faster. So, this is again just to show what is the path it has found. Sorry, this is a path that was found by best first search algorithm. We have seen this was the first algorithm we considered, and we saw that it found this longer path like this. It had only inspected 8 nodes, and the numbering is given here 1, 2, 3, 4, the order in which it inspects those nodes, and it had found a path of cost 195, which is much more than even what W A star has done. And the reason is that W A star managed to find this particular segment, which is much cheaper than this segment of coming down and then going up again essentially. I had asked you to look at branch and bound on the same graph, and I hope you did that at some point. Branch and bound extends the path with the lowest G values. The G values for this particular graph have been written inside the nodes here, and the G values have been computed as the best value for that path, because there may be multiple paths to a node. For example, for this node there are 2 paths, one is either coming from here or one is coming from here, but the G value and the parent pointer, it reflects the best path after the algorithm is terminated. Remember that branch and bound and Dijkstra's algorithm, they can reassign parents and update costs of nodes which are on open. So, this is what branch and bound does. It, in this particular example, it explores the entire graph, and that's in this case it is the entire graph, because the goal node is at one corner and all other nodes are closer than goal nodes. But even in a larger graph where the goal nodes were not in the corner, branch and bound would explore a larger amount of space than either A star or best first or W A star. It does not look ahead at all essentially. The goal it has found is optimal. Obviously, we have seen that Dijkstra's algorithm always does this, and if you compare this with A star, which we had also seen earlier, the same path is found by A star as branch and bound, except that A star has only seen a subgraph of the graph, which is depicted here. The nodes in orange are the closed nodes, which is much less than what branch and bound does, but which is much more than what best first and W A star do. It has inspected 14 nodes, but it has found the optimal path, and the reason for that is that its heuristic function was admissible. So, here is a comparison of the 4 algorithms. You can see that as weight increases in this table, with from 0 to 1 to 2 to tending to infinity, and as I said, when you write weight is infinity, it is equivalent to saying that the weight for G of n is 0, but it is just another way of saying this thing. The number of nodes that are generated, which means which are in open and closed, decreases as the heuristic, as the importance of the heuristic function increases. It starts with 23 and comes down to 19 and then 17. What is more important is that the number of nodes actually picked by the algorithm, that also decreases as the weight increases. As we have seen in this example, branch and bound inspects all the 23 nodes, but A star inspected only 14 of them, found a cost of 148, which is as good as the path found by branch and bound. So, it is clearly an improvement. Weighted A star saw 9 nodes, picked 9 nodes, but it found a more expensive path of 153, and branch and bound saw only 8 nodes and found a much more expensive path, and that is because we saw that at one point it was coming down and going up, and ignored one node which W A star did not ignore. And in the next session, we will look at variations of A star which are admissible. We saw that W A star, for example, did not find the optimal path, Now, we are going to focus on variations which will find the optimal path, but do some kind of saving, and in particular we will see that the savings that we are interested is in space. Okay. So, we will do that in the next session.